All right, thank you for the introduction. I'll move right along to just giving a brief introduction about where we're going, taking us back out beyond the solar system, thinking about M-dwarf stars again. It's already been said, but M-dwarfs are the most numerous stars in the galaxy. They comprise about 3/4 of the stars in our local neighborhood. But the other thing to keep in mind is that their planets are also extremely common. The terrestrial planets around M-dwarfs probably number every M-dwarf probably has a planet, and most of the M-dwarfs, or at least half, probably have several. And so this is borne out by statistics from the Kepler mission and others. Furthermore, these nearby M-dwarf planets will be essentially the only types of terrestrial planets accessible to James Webb in the next 5 years, and to the ground-based instruments as well. So this is another big reason to be thinking about terrestrial planets around M-dwarfs. And there are two reasons for which they're the best for, or the only accessible ones for James Webb. Ooh, I did that again. Is that because the terrestrial planets are larger on the disk of a smaller star, that makes the transit depth much larger. Furthermore, they have, this has already been mentioned, their habitable zones are much closer to the star, so they orbit more frequently, so you can co-add data more easily in a limited duration mission like James Webb. However, these planets are not without their problems. They likely face significant challenges from the pre-main sequence evolution of the M-dwarf host stars. The super-luminous phase can last for up to 1 billion years for the smallest M-dwarfs, and this can result in many oceans lost. Some work, my work is up to 20, other work like Volmont and Schaefer might be less, depending on the planet and parameters. You can also build up to thousands of bars of oxygen. And then, as Robin Wordsworth mentioned in one of his previous talks, the abiotic generation is probably very robust, but what happens to this afterwards? Perhaps the magma ocean would draw a lot of this down, or some of it might be lost to space. But we also need to think about atmospheres that may have some of this left. That's not the only problem, though. You also have lifelong stellar activity, including a larger percentage of UV and frequent flares, which may strip the atmosphere and sterilize the planetary surface. Also not so great for considering a habitable climate. So this means that there's many questions we want to ask initially to kind of do an initial assessment of what these planetary climates might be like. First of all, do they even have atmospheres? I know some people, in particular the atmospheric loss community, like to argue that no M-dwarf terrestrial planet will ever have an atmosphere. We really hope that that's not true, and we need to also think about how we can first assess that. Secondly, are these massive oxygen atmospheres that we've posited in different groups in the last few years, are these even possible, or are they quite common climate states around M-dwarf stars? Or our friendly neighborhood Venus. Perhaps we have lots of Venus-like planets around M-dwarfs because they all went into runaway greenhouse phases during the pre-main sequence phase. Maybe that's what we're left with. We also want to think about a habitable climate. Perhaps you can have a more hydrogen-rich planet that has migrated in early on. The pre-main sequence phase may strip off a lot of that hydrogen and leave you with a volatile-rich, habitable, evaporated core. So that might be the best route to habitability for these planets, but perhaps not the only route. But nonetheless, James Webb will provide us the first opportunity to distinguish amongst these and other evolutionary histories for terrestrial planets. And of all the different M-dwarfs, I know we've had a conversation about this in one of the undiscussions yesterday, but TRAPPIST-1 is really probably the best place that we know of so far to assess this. It's an excellent laboratory for studying planetary evolution and climate within a single system, because you have the three, if you follow the conservative habitable zone, you have 3 planets inside the inner edge, then you have 3 planets within the habitable zone, and then 1 beyond the outer edge. So you have a nice sequence of planets in and around the region that we're most interested in to assess in a single system. I should also point out there's been some discussion also of densities. These planets are all roughly Earth density from TTV measurements. So the error bars are still quite large, but that puts us in a good place. So for the remainder of the talk, I'm going to tell you just briefly about the models I'm using. I'll show you some of the climate and photochemistry results, and then I'll show you how we may distinguish among these environments with James Webb observations. So first, I'm using a 1D, very rigorous line-by-line radiative convective climate model. Convection is using mixing length theory. This has been coupled to a photochemical kinetics model, and I know a lot of people like using the 3D models, and it's great to get the spatial coverage, but we really are interested in what the chemical effects are in the atmosphere. Photochemistry is really important, so we have used this model to do this. And as I mentioned, the photochemical effects are important because, as some of the stellar people have pointed out, the stars do interesting and crazy and different things. We can't just assume an Earth-like atmosphere with Earth-like constituents, because these things change as a result of the different UV flux. The NUV might be much larger from the G dwarf at the same installation, but the M dwarf puts out a lot more in Lyman alpha and the high energy FUV. And so this is a really important thing to consider with photochemistry. And then, of course, the climate might be more driven or partially driven by the different SED. And that is captured by lots of other climate models as well. But the SED does drive photochemistry, and this does impact planetary climate. And so this is something that is crucial to understanding what we may observe by James Webb if we're looking at these planets. So we've talked a little bit about what the M-dwarf evolution might look like in terms of Venus-like or oxygen-dominated. And so I'm positing several different environments. I think, like Nancy King might have mentioned, that when we're doing some of these simulations, we can't just evolve something from Earth to Venus directly in our models necessarily. So we take different types of snapshots as to what could be a stable climate state, or perhaps these are end states. And so I'm starting with this posited, super desiccated, oxygen-dominated atmosphere. You've completely stripped off your entire ocean. There's nothing left. That's really sad. But this is one case we're looking at. We're also looking at, okay, this happened during the pre-main sequence phase, but say you still have lots of volatiles in your mantle and you start to outgas some of this. So we include some outgassing fluxes under an oxygen-dominated atmosphere. And then we also do model a photochemically consistent Venus-like atmosphere with the Venus trace gases, and we do include the chlorine chemistry. So this spans kind of a recent ocean loss to more outgassing over time, and that gives us a little continuum to check. And that the reason for this is that these planets, these types of atmospheres may be very common, and they're definitely not like Earth. And these could also exist because of the extent of the pre-main sequence evolution would have also hit as far as H during that time, so that any of these planets, including those in the habitable zone, may have atmospheres like this. And of course, these aren't habitable for the life that we know to exist on Earth, but we need to consider that these are the things we might actually see. But for comparison, both with these uninhabitable atmospheres and particularly with the 3D GCM results, I also include a 1-bar aquaplanet with Earth-like geological fluxes. So these different environments can result in very different temperatures, and as a result of the evolutionary history and compositions. I put here the habitable zone marked with the nice colors to tell you whether they're too cold or too hot for a habitable environment. And you see that even within the habitable zone, that you have lots of different temperatures as a result of the different types of environments you get. You can kind of see too that the habitable zone is sort of a good first order indicator of more of the habitable temperatures are within this range, but you also have, if you have a Venus-like atmosphere, it's going to be too hot. Others might be too cold if you don't have enough greenhouse gases. And also interesting is you can also get, if you have a Venus-like atmosphere on H, it may also be very hot as well. And this may result from the fact that these may be hot start planets, where after the pre-main sequence phase or even during it for H, you could have generated this kind of atmosphere and it would have started hot, and then it would not have necessarily cooled down after that. Now moving on to some of the more specific climate results. As I mentioned before, climate's not just about the surface temperature. Here's some temperature profiles and mixing ratio profiles of some of the key gases. This is for the completely desiccated atmospheres. You get a really interesting surface temperature inversion. This is because of absorption by both ozone and by oxygen collisional induced absorption towards the surface. So that causes interesting inversions you would potentially see in thermal emission spectra. You get some ozone buildup. There's no hydrogen or water vapor to scrub out ozone, so it can build up significantly. Now, if we include outgassing, which we hope or think is perhaps a more realistic case, things change quite a bit. Your surface temperature inversions tend to go away because now you have a lot more water vapor in the lower atmosphere. This heats the temperatures up. This is at least 100 Kelvin hotter than the desiccated cases. Water vapor profiles, again, the outer planets under these types of atmospheres too cold. You don't get much water vapor. You still have ozone, but it can be reduced a little bit. CO2 is, I use different levels of CO2 here considering an outgassing case, but I don't have geological feedbacks here, so this might be very different. These are just different CO2 levels you might experience. Now, these outgassing planets also are affected by aerosol formation. I should note here that I don't have TRAPPIST-1b on this plot because TRAPPIST-1b ends up being too hot in our models to condense sulfuric acid clouds, which are the clouds I'm condensing here. So that's kind of an interesting result as well. You get more Venus-like temperature profiles, though perhaps warmer in the stratospheres because the Mdwart SED is more in the near-infrared bands, and so you're absorbing a lot more in the upper atmosphere. You also find that SO2 is quite a bit more resilient around M-dwarf stars than it is around the sun. Here's the SO2 profile in our model around the G-dwarf, and that's also consistent with other Venus models. And so you end up forming sulfuric acid vapor around these atmospheres, both the outgassing ones and the Venus-like atmospheres. And here's our optical depth profiles. Now, if we look at this, maybe a more easier way to think about it is just the total optical depth of each atmosphere. We end up finding that, yes, TRAPPIST-1b is not shown because it doesn't have any, but even TRAPPIST-1c might be slightly too hot. And TRAPPIST-1c gets slightly more insolation than Venus. So it maintains optical depth 1 roughly clouds, and then D is a lot stronger because it's vigorous but also cool enough. So how may we distinguish between these different types of atmospheres with spectra with James Webb? Show you just one example plot. It's hard to look at spectrum talks like this, so I'll just point out back to our original questions, right? How may you first tell that the planets have an atmosphere? CO2 lines are quite common amongst all these atmospheres. We pretty much assume that CO2 is in most terrestrial atmospheres. We see that in the solar system, so you can look for these lines. Now, how may you distinguish between different types of environments? You see collision-induced oxygen absorption, which would indicate a heavy oxygen atmosphere, so you might be able to find a massive oxygen atmosphere that way. You have other discriminants here of the various atmospheres, whether you have water vapor or some of these lines are CO2. You might see SO2 in different types of atmospheres that may indicate a drier atmosphere like Venus, and so forth. Ozone is not necessarily an indicator of an Earth-like atmosphere as well. You get those in the high oxygen atmospheres. So it's important to think about how you may discriminate these as well. Now, these are beautiful perfect spectra. This isn't what James Webb is going to actually show us. So let's show some results from my colleague, Jacob Lustig-Jaeger, who uses the James Webb simulators and assesses what's the best way to look at these things. And so here's one example. This is the O2 outgassing case, and we find that characterizing hot terrestrials such as TRAPPIST-1b is quite possible with James Webb. Some people I've heard in the community might be saying, oh, we can't do terrestrials with James Webb. That's really not true. Here you get signal strengths of up to 200 ppm, which is a signal noise of perhaps 10 over the putative noise floor. And so you can see CO2, you can distinguish water. You can even, if you look closely, and if maybe I plotted this wider, you get pretty good signal on the O2 bands as well, O2, O2. So you can start to distinguish these atmospheres with James Webb. So now I'll show one more. We'd like to think about the climates more of Earth-like planets or ones in the habitable zone. This is a lot more difficult, and this will require many repeated observations. So it could be that we have to take measurements over the entire life of James Webb to look at this. Here you get, again, signal noise 5 on these features, and you can actually distinguish some of them, but this requires a lot of transits, 50, perhaps 30 or 50 for a clear sky atmosphere, or hundreds of transits of a cloudy atmosphere to start to see some of these bands. And so just in conclusion, stellar evolution helps determine the planetary atmospheric composition, and that these planets may have these heavily evolved atmospheres like we see on Venus, with oxygen possible as well. And that this atmospheric composition does affect climate at a given installation, that even habitable zone planets could have a very large range of surface temperatures that really depend not just on perhaps some of the geological cycles, but also the pre-main sequence evolution of the star and how much volatiles were available. And that most importantly, I think, is that, and we all hopefully would like and agree with, is that observing terrestrial planets with James Webb is possible, and so we should be doing that. And I think there are GTO observations for TRAPPIST-1 that will occur, and that this is a great system for comparative planetology that allows us to study different evolutionary states. Thank you.
We have time for maybe one quick question.
Good talk. When your models produce estimates for surface temperature, is that for the day-side average or substellar or what?
That is global average, right? And so that's one reason why I also only did 10 to 100 bar atmospheres, is a lot of the 3D models show with thinner atmospheres that might be more difficult, and that you have more day-night temperature contrast, but we would expect atmospheres like this to be a lot more Venus-like and to have a much more uniform. So this is global average temperatures. Yeah.